Good day. Today we're going to tackle about the inscribed angle theorem. Before we proceed to the inscribed angle theorem, we first need to define what theorem is. Now, theorem is an important statement that must be proved before it can be accepted. So this is the definition of theorem, and we need to prove each statement that is considered a theorem. So the inscribed angle is an angle whose vertex is on the circle and whose sides are chords of the circle. So meaning, in the illustration, the vertex of this angle should be a point on a circle, and this side of the angle should be considered as a chords of circle. So in this case, this is an example of inscribed angle. And where the sides intersect to the with a circle, this is the intercepted arc. Now, let's see this illustration. Can we consider this as an inscribed angle? Yes, it is an inscribed angle. As you can see, the vertex lies on the center on the circle, and the sides are chords of the circle. How about this one? This is not an inscribed angle because the vertex is outside the circle. How about this one? Again, this is not an inscribed angle. Though the vertex is on the circle and one side is chord of the circle, the other side is not a chord of the circle. That makes it not an inscribed angle. There are three kinds of inscribed angle, or we should say a cases of an inscribed angle. So case number one is an inscribed angle that has one side of the angle is the diameter, meaning it contains the center of the circle. So this is a diameter, and the other side is just a chord. So this is our case number one. This is the illustration of case number one. For case number two, or example number two, the center of the circle lies in the interior of the inscribed angle. So this is the center, and the sides of the angle is this, and so that makes the center of the circle inside this inscribed angle. So this is case number two. For our last case, case number three, the center is in the exterior or outside of the inscribed angle. This is the inscribed angle, and the location of the center is outside of it or in the exterior of it. So these are three cases. Now, by definition, or by theorem, the inscribed angle theorem stated that the measure of an inscribed angle, which is this, is equivalent to one half of the measure of the intercepted arc. So meaning in this illustration, the measure of angle A, BAC, this is angle A, is equivalent to one half of the measure of BC. So if this is 20 degree, so this is 40 degree. One half of 40 is the measurement of this angle. Again, this is a theorem and we need to prove this. We're going to prove this using the three cases or the three examples of the inscribed angle that I shown you a while ago. Now, in order for this statement to be acceptable, we need to have a proof for each cases or for each example. And for now, let's go with case number one. Here, the diameter is a side of the inscribed angle. So given angle ARO is inscribed in circle D and AR contains D, that makes AR a diameter. Now let's prove that angle ARO is equivalent to one half of the measurement of arc AO. So first, let's draw an auxiliary segment which we name DO. As you can see, I write it in a broken line to emphasize that this is an auxiliary segment only, meaning I'm the one who write this. And next, let's name ARO as x or x degree, the measure of ARO. So by this point, we can say that angle ADO is a central angle. And the measurement of these central angles is equivalent to the measurement of AO, meaning that these two are congruent. So how can I say that is congruent? It's because of the central angle intercepted arc postulate. So if you want to know more about that postulate, just go back to my previous video about central angle and intercepted arc postulate. Now, as you can see, we created, because of this auxiliary line, we created here a triangle. Now, this triangle is an isosceles triangle. Why did I say that is an isosceles triangle? An isosceles triangle is a triangle that has two equal sides. So this is an isosceles triangle because DR and DO are radii of a circle of the circle. Therefore, it has the same length. And now that the DRO is an isosceles triangle. Now, because if it is an isosceles triangle, meaning two angles of this triangle are also congruent. So if the measure of this is x, therefore the measure of this is x as well. So that's the that's the definition of isosceles triangle. Now, by exterior angle theorem, we can say that the value of this ADO is equivalent to the sum of these two angles. If you have a triangle, it's regarding the size of the triangle, and you have a line here, the measure of this side is supplementary to this side. And I should say that the measure of this is plus the measure of these two is also equal to 180 degree. So therefore, if we add these two angle, it is equivalent to the measure of this angle. That's what happened to this angle. This is a straight line, and we created a triangle here. So meaning the measurement of this is supplementary to this. And the measurement of this plus the sum of these two is also supplementary to this. So therefore, the sum of these two is equal to the measure of it. That's why we can say that angle ADO is equal to 2x. And if that is 2x, then the intercepted arc, which is arc AO by our definition a while ago, is also equal to 2x. Now, we have a proof to our theorem. So therefore, because the measurement of AO is 2x, therefore the measurement of angle ARO is equivalent to 1/2 of AO because x is 1/2 of 2x. So this is our proof for case number 1. So I hope you understand this. This is the best way that I can show you the proof of it. And hopefully that you understand this. Next is I'm going to prove the same theorem in case number 2. Now in case number 2, angle PQR is inscribed in O, wherein O is in the interior of the inscribed angle or the center of the angle. The center of the circle is in the interior of the inscribed angle. Now I will give a proof, I will prove that the measure of this is equivalent to the one half of measure of this. Now let's first draw an auxiliary segment, name QS. Now let's name angle POQ as A and angle SQR as B. So we created two angles. Now by arc addition postulate, the measurement of angle PQR is equivalent to the sum of the degree of these two. So that's why we have this equation. Now on case number 1, a while ago, we proved that the measure of angle A is 1/2 the measure of PS. We already proved that because in case number 1, one side is the diameter. And also, the measurement of B is also 1/2 of the intercepted arc. That's also case number 1 because again, this one side is the diameter. So now by that, if we add AB, this should equal to the sum of PS to the 1/2 of PS and 1/2 of SR. Because that's the arc addition postulate and angle addition postulate. Okay? Because A is 1/2 FH and B is 1/2 SR. So if we add A and B, we just add 1/2 PS, arc PS, and 1/2 the measurement of arc SR. That's why we have this equation. Now, if that's the case, let's simplify it. Let's use common monomial factor and let's put out 1/2. Then after that, we can say that the measure of PQR is equivalent to A and B, A plus B. Since A plus B is equivalent to 1/2 PS and 1/2 plus MS, so we can just equate this to this because they are just equivalent to each other. So we have now a equation of this. The measurement of PQR is equivalent to 1/2 of the sum of PS and SR. Now, by arc addition postulate, we can know that if we add this, we will get PR. So, therefore, we can now prove that measurement of PQR is equivalent to 1/2 of the measurement of PR. So, that's the proof for case number 2. Now, for case number 3, the center of the circle is in the exterior of the inscribed angle. So now we will prove that the measurement of BAC is equivalent to 1/2 of BC. So how do we do that? First, again, let's draw a diameter, an auxiliary segment named DA. And let's mark the measurement of angle DAB as A and BAC as X. So by angle addition postulate, A plus X is equals to DAC. Now by subtraction property, we can, because we need to get the value of X, we can get the value of X if we subtract A to the measurement of DAC. So that's why we have this equation. Now on case number 1, we know that DAC, because it is a diameter, one side of the angle is a diameter, DAC is equivalent to 1/2 of DC. Same as with A. DAB is equivalent to 1/2 of DB. So that is case number 1 in action. Now, let's substitute the value of DAC to this equation and the value of A to this equation. Then we are given by this new equation. Now, if we're going to simplify it by common monomial factor, so we subtract DC by DB and we put 1/2 outside the parenthesis. That is common monomial factor. Now with that, we can say that DC minus DB is equal to BC. Arc addition postulate, then we do a subtraction property of inequality. Again, the measure of this minus this is the answer is this. And if you can see, they are the same. So therefore, we just change this with this because they're just equal. So therefore, the measurement of angle BAC is equivalent to 1/2 of BC. Now we prove the theorem that the measurement of the inscribed angle is equivalent to 1/2 of the intercepted arc in all cases of the inscribed angle. So therefore, with good heart and with confident, we can say that this theorem is true. Now let's go with some examples on how to answer questions involving central angle and intercepted arc. Now, for this example, let's solve for x. Since the measure of x is 1/2 its intercepted arc AB, we can say that x is equal to 40. Now, let's go to the next example. Now, let's find the measure of angle A. Now, again, the measure of angle A is equivalent to half of its intercepted arc, which is arc BC. So, what arc BC measures 50, so 1/2 of 50 is equivalent to 25. Now, for another example, let's find the measure of arc BC, where angle CAB measures 85. Now again, we know that the measurement of angle A is equivalent to 1/2 of BC. Now let's just do the opposite. Instead of we get the 1/2 of the given number, we just multiply it by 2. So we get 170 for the measure of arc BC because half of 170 is 85. Now there is another theorem inside inscribed angle theorem which state that the semicircle theorem, an angle inscribed in a semicircle is a right angle. So meaning in circle O, ABC is an inscribed in semicircle APB. So then ACB is a right angle. So it's actually obvious because if it is a semicircle, it measures 180. Then therefore the inscribed angle should measure 90 degree by inscribed angle theorem. So let's try to put this in an example. Now, as you can see in the illustration, DB is a diameter of the circle. So it divides the circle into half, meaning that this inscribed angle measures 180. Then, to get the measurement of angle A, we can get the 1/2 of 80, and that is 90. So angle A is 90 degree. Now let's find the measurement of angle C. Same example, BAD is a semicircle, therefore it measures 180 degree. Then 1/2 of 180 degree is 90. So that's the measure of angle C. Now let's find the measurement of arc BAD. As you can see, there is a symbol here of this. This symbol signifies that the measure of this is 90 degree. Since the angle is 90 degree, therefore we need to double it to find the measure of its intercepted arc. So the twice 90 degree is equal to 180 degree. So that is a right angle. So therefore, it should have a semicircle intercepted arc. That is 180 degree. Another thing is an inscribed angle in the same arc theorem. So two or more angles inscribed in a same arc are congruent. So meaning, just look at angle B, this angle, and angle C. They have the same intercepted arc. Therefore, they are congruent. That is the definition of this theorem. Again, let's put this in action. Now we need to find the measurement of this. If this is 40, therefore it is 80, and therefore it is 40 as well, because they have the same intercepted arc. So that makes measurement of angle A is equivalent to measurement of angle B. So that means angle A is also 40 degree. Same as with this example. If we find the measure of angle B, then these two angle A and angle B have the same intercepted arc. So if you have the same intercepted arc, therefore there are equal to each other. So angle B is also 50 degree. Now let's go to another theorem, the inscribed quadrilateral theorem. Opposite angles of inscribed quadrilateral are supplementary. Okay, look at this. This ABC quadrilateral, that is wherein angle A plus angle C is equal to 180 degree. That is supplementary angle. Now angle DB and angle D are supplementary as well, meaning the measurement of this plus the measurement of this is equal to 180 degree. Then how is that possible? Just look at this. The intercepted arc of angle B is this. So half of this is the measure of this, while D is this. Now half the measure of this is this as well. Now if this is the entirety of the circle and the one half of the entirety of circle is 180, therefore if we add these two, then they are equal to 180 degree. So as long as it has a quadrilateral inscribed in a circle, that the opposite angles of the inscribed quadrilateral are supplementary or equals 180 degree. Now let's put that in action. As you can see in this example, if we solve for angle A, we need to know what number we should add to 72 to get 180. So to do that, let's have 180 minus 72. That is 108. So 108 plus 72 is equal to 180 by that theorem. On the other hand, to solve for angle B, we need to know what are we going to plus to this angle to get 180 degree. Since this is 90 degree, so what the question is, what are we going to add to 90 to get 180? And the answer is 90. So that is the measure. That is how this theorem works. Now let's give a final and somehow average type of question. Now to find the angle x, first we need first to make a auxiliary segment which is HN. Now we can mark these two angles as angle A and angle B. Now we know that if we add angle A and the angle in front of it, we know that this equal to 180 degree. So therefore, angle A should be 80 because 80 plus 100 is 180 degree. Since it is a linear pair, meaning it is a line, if we add A and B, we can get 180 degree as well. So what are we going to add to A to which is 80 to get 180? And that is 100. So this is 80, this is 100. Now what are we going to add to this 100 to find the value of x? Again, if we add this, the measurement of this to the measurement of this, we should get 180. So opposite angles of inscribed quadrilateral. So b plus x is equal to 180, then b is equal to 100, then subtract 100 on both sides, we can get as x is equal to 80. So that's all for this theorem. I hope you enjoy and I hope you learned something. Don't forget to share this to your friends and like and subscribe. Thank you.